So we're going to look at another problem involving binomial random variables. In particular, we want to see if the current problem here, number 40, represents a binomial random variable, and if so, can we answer questions based on binomial probabilities for A through E. So, okay, we'll see. Now, the first thing to do is to check if it fits. Is there a fixed number of trials? Yes, 580. Are they independent? That one, we're going to kind of have to assume that the results are independent from one offspring to the next. There are two outcomes, yes, either yellow peas or not yellow peas. And finally, the same probability. We're told to assume that Mendel's claim of 25% is true, so that would mean that there's a 25% chance throughout the experiment that you're going to get a yellow spring pea or offsprings. These plants are going to be yellow peas. Tongue-tied there. So it says first part is to use a range rule of thumb to identify limits separating values that are significantly low and those that are significantly high. So that's a good question to start with because it's going to require us to know a few things. Remember the range rule of thumb? Rule of thumb is going to look at the values between 2 sigma below to 2 sigma above, like that. And that requires that we actually know the mean and standard deviation for this binomial random variable. So how do I calculate the mean of a binomial random variable?
Would that be n times p?
Excellent, thank you. N times p. So in our case, 580 times 0.25, that's multiplying by 1/4, so that's 145. Okay, thanks, Laura. Someone else here. How do you find the standard deviation of a binomial random variable?
Square root of n, p, and q.
Beautiful, n, p, and q. Now, I know that p is 0.25, so what does that make q equal to?
0.75.
Perfect, thank you, 0.75. So square root of n times p times q, 580 times 0.25 times 0.75. So the square root of 108.75 is about 10.428. Perfect. So now we're in shape to calculate the range rule of thumb. I want to find mu minus 2 sigma to mu plus 2 sigma. So 145 minus 2 times 10.428, 428 to 145 plus 2 times 10.428. Let's see what that gives us. So pull out a calculator for that one. That should give you about 124.144 to 165.856. All right. Let's understand that from a practical point of view a little bit more. So kind of draw that out here. All right, so let's see. We had 124.114, or 144, and then 165.856. Now, when you're looking at the number of yellow peas in the offsprings, can you get 124.144? Is that a possibility in terms of results you can get from this binomial random variable?
No.
No.
No. Thank you. So, Joseph, what are some values near this that I can get?
You can get 124. It rounds closest.
124 and 125. Thank you. And some other ones over here would be 165 and 166. Right? Now, the thing to be careful of is what's where. So, is 166, is that a typical result or is that significantly high?
Significantly high.
Yes. And likewise, this is significantly low. So let's label those appropriately. Significantly high and significantly low. So that means the stuff in between then, between 125 and 165, those are not significant. I like to call them typical, but I'll keep in line with the book, not significant. Beautiful. How are we looking on that one? Okay. All right. So there's some more parts to this problem. Let's take a look at it. Part B says, find the probability of exactly 152 P's. By the way, I guess there was a little more to part A. Is the result of 152 P's either significantly high or significantly low? Well, what do you think? Where does 152 P's fall?
Not significant.
Yeah, 152 yellow P's is neither significantly high nor low. Yeah, it's kind of in that middle ground there. And that's fine. Nothing special about 152. But let's find the probability of 152. Now remember, what we would typically see is that an event is statistically significant if its chance of it happening is less than 5%. So for part B, we want to calculate the probability that X equals 152. Well, you've got a couple possibilities. You could do that with Google Sheets, or you could do it with your graphing calculator. Let's do it on Google Sheets first. So I'll type in equals, start typing in binomial distribution. And once it narrows it down to what I want, I'm just going to hit the enter key. Now there's a couple things I need to know here. I need to know N, P, and X. So N, P, and X. Let's see what those are. So N was 580, P was 0.25, and there's your X, 152. All right. Sometimes I get these commands a little confused. On the test, what I'll do is I'll have the list of these commands up there for you at the top of the sheet. In fact, here's kind of a quick look at what you can expect. So here's all the Google Sheets commands that I think you could use. Then here's the appropriate graphing calculator commands. So the whole idea is that you shouldn't have to remember, the exact form of the commands. I'm not testing you on Google Sheets. I'm not testing you on the graphing calculator. You do need to get results from these things, but that's not really the point of these problems. The problem is to interpret the results. So let me go back over to here. As far as the binomial probability is concerned, I want to type in 152 So your x, then your n, and then your 0.25. And I'm going to type in false. Now, what's this false doing? False just says that I don't want to add up all the probabilities of everything less than or equal to 152 happening. I just want this one probability, not all the probabilities before it and including 152. And now I get, geez, I get 1.0301. That's not very big. In fact, it's less than our typical 5% threshold. Now, is anyone going to be doing this on the graphing calculator? Any graphing calculator fans out there?
I did it on the graphing calculator and I got the same answer.
Same
Okay.
here.
All right, good, good. So on the graphing calculator, this should look like this. Let me clear out this stuff here and here. Oops, there. So you hit second, and then distribution, then you go up 6 or 7 times, depending on your calculator, to binomial PDF. You don't want CDF, you want PDF. We'll use CDF for a different part of this problem. There's 580 trials. Probability of success is 0.25. Our X is 152. And yeah, 0.0301. Beautiful. So how are we looking on that one? Pretty good? All right. Let's look at the next part of this then. So the next part of this is going to ask us to think a little bit. Find the probability of 152 or more yellow peas. Wow. If you think about that, that could require a lot of work. So probability-wise, what that's asking us to do is calculate the probability that X is, what symbol should I put in here?
Greater than or equal to.
Greater than or equal to, thank you. And that would mean probably that X equals 152, or X equals 153, or all the way up to X equal 580. And even on Google Sheets, to try and do it kind of by this brute force approach would be really tedious. You'd have to calculate a lot of different probabilities. I mean, it's quite doable. It just takes a little bit more finesse than I want to employ. So, there's actually a better way to do this. And we can kind of get a glimpse of that by looking at the old exam. So online, one of the questions I gave you was this one. So you have a genetic disorder, you have offspring that could have that genetic disorder, and you're looking at the probabilities involved of having so many kids with that genetic disorder out of 4. And one of the problems that I asked is, what's the probability that at most 3 of them have the disorder? Now, one way you could answer that problem is just simply add up 0, 1, 2, and 3, which isn't hard for something like this at all. But the idea that I chose here to use was I used the complement rule. Instead of doing, adding up all 4 of those, I said, you know what? Let's use the complement. It's going to be 1 minus the probability that X equals 4. And I get the same thing. It's not a big deal there, but it is here. So let's try and understand this problem a little bit more. This problem of trying to find the probability that X is greater than or equal to 152. So, Draw ourselves a little scale here. And we'll label a couple of the extremes. We have 0 down here, 580 up here. And then somewhere about 1/4 of the way through, you have 152, 153, 151, etc. The probability that we're trying to get is X is at least 152. Now that means that it includes 152. So I want all these guys here. So if you want to call this, I don't know, set B, that's fine. But calculating that directly would be a lot of work. So what other choice do I have though? Well, I'm glad you asked. Another possibility would be this. If you like, we can call that B bar. Now, what's the advantage of B bar? Can you just explain what B bar would represent? What would I be? What is this really saying? What type of events?
Everything but B.
Everything but B, good. Now B is probability that X is greater than or equal to 152. I should be able to calculate this with the complement. So what's the complement? Well, it's going to be 1 minus a different probability. What's that new probability? What would be?
X is smaller to 152.
Good, X is less than 152. And in fact, because we're not including 152, that'd be X is less than or equal to 151. Do you agree with that? So you're either here or here. But the probability of this, probability that X is greater than or equal to 152, is 1 minus the probability of the complement, or that X is less than 152. So I just want to sit here for a moment till I see that you're okay with this one.
Is that just the second equal sign with the 1 minus P of X? It's just a different way of writing it, or that's technically the correct way?
Well, these two are equivalent because X is less than 152 doesn't include 152, does it?
Oh, yeah, I guess. Yep.
So by putting the less than or equal to, now I've got everything starting here and going over. So it's just two different ways to write the same thing.
Okay, thanks.
No, appreciate the question. Thank you. Anything else on this much? Because I mean, this is the important part to understand here. Is doing it this way, using the complement rule. Because right now I'd have to calculate 428 different probabilities, 429 different probabilities to calculate this. Here, I'd only have to calculate 152 probabilities. So it's better, it's still a lot of work, but there's something more that we can do here that I couldn't do here. And that is, I can use this command with a true. And let's see what difference that makes. Remember we did this the other day when we replaced false with true, it added up these probabilities all the way up to whatever number this was. So let's take a look at it back with our Google Sheets. If I want the probability that X is less than or equal to 151, I can do that on Google Sheets here. Let me do it next to our other calculation. So it's going to equal binomial distribution of 152, actually, no, 151, comma, 580, comma, 0.25, This time I'm going to hit true. And that's going to add up all the probabilities up to and including 151. That's not quite the probability that I want yet, though. It's close, but it's not the final answer.
You just subtract that by 1, right?
Yep.
To get
So
the-
over here, I'll do 1 or equals 1 minus, and I'll click that cell. That way I don't even have to copy it. So the last part would be to subtract it from 1. Thank you. So 1 minus 0.735. So we'll end up with about 0.265. And on the test, I'll specify how many digits that I want. And if I don't, you're free to give me whatever you want. Shame on me for forgetting. Likewise, you can do that on a graphing calculator. So the command that you would want to use on a graphing calculator is not the binomial PDF, it's the binomial CDF. And I hope that I'm not overwhelming you with terms and technology, but you just can't really do this by hand in any efficient way. So second distribution, again, I'll go up. This time I want to go to binomial CDF. Number of trials, 151. P-value, 0.25. Actually, no, wait. Number of trials would be 580. 580. And then X value is 151. Enter. Now I want to take 1 minus that. So fancy way to do that, you could hit the 1 minus. Well, I want to take 1 minus the previous answer, so let me just go up there and grab that. So I'll hit the up arrow and press enter. It brings it down and puts it where I want it. There you go. 0.265 again. Cool. How are we doing with the calculation of this?
So the 151, like, that's just the number that we go up to, right? Like when
That's
we say-
correct.
Okay.
Yeah, because we get that from the complementation rule.
And that
So-
includes the 151, because you
It
said like,
includes the 151. Notice I was careful not to include the 152 because that's part of the other set.
okay.
Yep.
Yeah.
Thank you. Thank you. Anything else on this much of it? I believe there's a little bit more we've got to address here. Last chance, though, if there's something that you're unsure of. Okay. Which probability is more relevant for determining whether 152 P's is significantly high? The probability from part B or part C? Based on the relevant probability, is the result of 152 yellow P's significantly high? Okay. So, well, what do you think? If I'm looking at the result of 152 yellow P's, should I be looking at part B or part C to try and determine if this is unusual in some ways?
Would you look at part B?
C? I think C.
Non think C? Laura, were you going for B?
Yeah, I think so.
Okay. How about somebody else? Break the tie.
I think B.
I would say B.
I say B.
A lot of people saying B. Well, non, good on you. The result's actually C. Because what's going to happen is the more and more events you have, the smaller that each of these probabilities is going to get. And eventually you're going to have so many events that every event is going to be a rare event. So to try and get around that, what we're going to do is we're going to look at the possibility of this event or something more extreme. So by looking at this probability, we see that, yeah, 152 is not really rare, okay? 152 or more. Whereas if we just look at one particular probability, you know, the actual probability there was 3%. That's less than our typical 5% rule, saying that, okay, that's a significant event. But, you know, it's not really a significant event. We looked at the range rule of thumb, and the range rule of thumb said that, yeah, that's in the typical range, right? 152 was almost dead in the middle. So it wasn't significant. And when we look at this probability for part C, again, we see that it's not a significant result because it's going to happen, you know, more than 25% of the time. So this is going to be something consistent throughout this book, is that we're going to look at the probability of something in what I call the tail, this or something more extreme to the right or more extreme to the left, depending on the problem. So this is something to kind of get used to as we move forward. It's not going to be something I'll test you on, you know, too much right now, but it is going to be part of what we're going to work on later on. So the answer to part D is C, is the more relevant probability. What do the results suggest about Mendel's claim of 25%? Well, they're consistent with his claim. Okay, so we didn't see anything that suggests that his claim is wrong. Does it prove his claim is right? Not really, but at least we feel pretty comfortable with his claim. There's nothing to suggest that he's wrong with his claim. And that's about the best we can say here, is that, yeah, the results are consistent with his claim. But the difference between math and statistics is that in statistics, we're never able to say we proved something. The best we can typically say is we're pretty sure that something's right. We're 95% confident that we're correct. There's a 5% chance we're wrong. Those kind of things. But in a stats class, we're never going to say, yeah, we proved something right or we proved something wrong. It just doesn't happen with statistics. Anything else on problem number 40? It's a good one. And I hope that you got a lot out of it. I mean, we started out by looking at whether or not this was a binomial random variable. We calculated the mean and standard deviation. You should be able to do that. We use the range rule of thumb to identify significantly high, significantly low. Again, that's stuff you should be able to do. And finally, we calculated some probabilities. And in particular, I like this problem because we use the complementation rule. That's pretty key. And we also used Google Sheets to come up with this probability pretty quickly. You can also use a graphing calculator. Graphing calculator will work on that as well. But it's just one way or another, it takes a little bit of thought to be able to get that probability out of our technology. You don't want to have to do that by hand.
I have a question with D. It says it ends the question ends with like whether it's significantly high or not. Would it be considered significantly high since we're using part C?
No. It'd be significantly high if the chance of that happening was pretty small. Then it'd be a significant event. Because our probability of this happening was 0.265, that's not a small enough probability to rate this as a significant event. Significant events are events that have a chance of happening of less than 5% is our typical level at which we say, okay, that's starting to be unusual enough that we'll call it a significant event. So because this one didn't meet that threshold, it wasn't less than 5%, we said, all right, that's not a significant event. So great question though. Did my answer work for you?
Yeah, somewhat.
Somewhat. Well, so
I have a question about that also. Would it
Yeah.
would it be fair to say then, instead of significant, rare event?
yeah. So one of a couple things happens when you're looking at these kinds of probabilities. This calculation is assuming that Mendel was right, that we had a 25% chance of getting a yellow pea as an offspring. All right, if that calculation or if that assumption is true, then yeah, all right, we didn't observe anything terribly unusual or rare. Now, if this probability were smaller, say 0.0265, so that it was less than our 5% rare event rule, then what we could say is that, well, yeah, it looks like we observed something statistically significant or very rare. Another conclusion would be that our assumption was wrong. And what we're going to do later on, especially with our hypothesis test and the rest of this course, is if we get a probability that's really small, less than either a 5% or 1% threshold, we're going to conclude that our assumptions were wrong. Now, the assumptions in this calculation were that we had a 25% chance of getting a yellow pea. So if our calculation led to a really small probability here, we'd say, yeah, you know what, our assumption was probably wrong, because this just shouldn't happen. So Marge and Shane, I was trying to address both of your questions on that answer.
So significant kind of means like a rare event.
Yep.
That makes more sense now, I guess. Thank you.
Marge, doing okay there?
Yes, totally understand. The significant, it was messing with me with the 5%. So thinking of it as a rare helps me understand less than 5%.
That's great. Perfect. Thank you. Okay. Nice. Somebody was asking earlier about problems with the Wi-Fi and getting kicked off. Just a reminder, OCC is open so that you can use their Wi-Fi from 10 a.m. to 7 p.m. during the week. So if your Wi-Fi is not reliable and you want to just sit at OCC, you should be able to go to OCC and use the Wi-Fi there. I mean, it's a lot of bandwidth. It's pretty reliable, and I don't think there's very many people using it. So, all right, all done with that one. Okay, I think we'll call it a day on our work with section 5.3. So make sure you're ready for that kind of a problem on the exam, and the exam is next week.